Welcome to the AP Calculus AB video for Skill 139. I can apply differentiation rules within the context of rate of change. And the trivia question for the day is the curl that you see at the top of this capital, or you could call it a scroll, which exists at the top of some capitals, is trademarked with what order of Greek architecture? Alright, so for this skill what we're going to be doing is we're going to be using differentiation in the context of rate of change. So it's not really any new rules. Basically it's applying context to what we know about differentiation. So for our first example, what it says is find the rate of change of volume of a sphere with respect to its radius. So the rate of change of volume with respect to radius. So what they're saying is, what is the rate of change of volume with respect to its radius? Or you could think of that as take the derivative with respect to r of a volume function. So since we're looking at a sphere, our volume function for a sphere is 4/3 pi r cubed. And if we want to take the derivative of that with respect to r, we can use the power rule, drop the 3 down in front, and it simplifies out to be 4 pi r squared. So that means our change of volume with respect to radius is 4 pi r squared, and they ask us to evaluate that when the radius is 6 inches. So we plug 6 into that and we get an answer of 144 pi. The tricky part here is trying to understand units, and what we have here for units is volume. Volume is a cubic inch calculation, so cubic inches, or if you want to write inches to the third, and our radius is a inch unit. So the unit we're looking at is cubic inches per inch. So roughly translated, what this means is that when we have a sphere with a radius of 6, if we were to add another inch to it, we would approximately be adding 144 pi cubic inches in volume. Now that's kind of your instantaneous right at 6. That'll change, of course, as our radius grows. Alright, the heart of this lesson is in this next piece, which is the relationship between position, velocity, and acceleration. So if we have a function we'll call position, which is s of t, the velocity is the derivative of that function. So you can imagine here we start at this point and we kind of move along here and we get over to this point. The secant line which connects it would kind of be our average velocity, or at any particular point we might be able to get our instantaneous velocity. Going beyond that, acceleration is the derivative of velocity, so the rate at which our velocity is changing is acceleration. A lot of people know position, you could say, is miles, and velocity is miles per hour, and then acceleration is going to be miles per hour, which is kind of a weird unit. Those who have done physics might be familiar with the meters per second or meters per second squared. It's not really a unit that our brain can grab onto. But the relationship is the derivative of position is velocity and the derivative of velocity is acceleration. Then we have this other word that we use, which is speed. Speed is not the same thing as velocity. Velocity is our speed with a direction. So whereas speed is just the magnitude of how fast we're going. So the way we find speed is we take the absolute value of velocity. In essence, we're removing the direction aspect of that value.
smile for the camera.
No, yeah,
I'll take one photo.
No, I hate cameras. I already told you.
One photo.
Yeah, man. Yeah.
3.
Don't take the photo, man.
2.
I don't like photos,
1.
man. Did you take the photo?
Nah,
I liked it.
I took it.
Nah, take it.
Yeah, I'll take a second one, okay?
Huh?
Yeah,
Nah, no more.
It was pretty good. One
Nah, I don't
more.
like photos. No more. We have to go. Let's
3,
go.
2,
Nah, hey, man.
1.
So jumping into example 2, what we have is a position equation, and this is a pretty common starting point for assessing whether students understand this skill of the relationship between position, acceleration, and velocity. And we use the position equation and ask lots of different questions about it. For example, find the displacement after the first 4 seconds. So the displacement is going to be like, here's your position at time 0, and here's your position at time 4. What is the total distance between the two, which is your displacement? So you can just say, what is the position at 4, subtract the position at 0, and we get a positive value, so you can say the particle has moved 50.6 units to the right. We don't know whether or not the particle went all the way over and then came back. That's something we explore later on, but regardless, its displacement would still be the same as whether it was in case 1 or case 2. The next question, very, very common, when is the particle at rest? So an object is at rest if the velocity is 0, and that kind of makes sense. If there's no velocity, it's not moving. So what we do is we find the velocity equation, and we do that by taking the derivative of our position. So the derivative of position leads us to 2t squared minus 20t plus 42. And if we want to set that equal to 0, one of the tricks that we should use is perhaps factoring it out. And we find that once it's factored, we can set it equal to 0 and find that at time 3 and time 7, the particle is at rest. The next question is, when is the particle moving to the right? So basically, when is velocity positive? And so we can set the velocity equation equal to 0, and we find that those times 3 and 7 are important, and we can find that the velocity is greater than 0 if our time is between 0 and 3 seconds or after 7 seconds. So basically from time 0 to time 3, it's moving to the right, and then it's going to start coming back to some spot. Where it is, we don't know, but at time 7, and then it's going to start moving to the right again from 7 to infinity. Alright, moving to the next page. When is the particle speeding up or slowing down? So this concept of speeding up or slowing down is a struggling point, but if you can just remember, an object is speeding up if both velocity and acceleration have the same sign. So the way that I set up to determine whether or not they have the same sign is I'm going to find the intervals where their sign changes. And so the first thing we did is we already know that the sign changes for velocity at times 3 and 7. So we have time 0, time 3, and then time 7. And then we also look at acceleration, and we find acceleration is 0 at time 5. So what I did is I set up this little window, this interval of time, and I looked at what was going on within each interval. So from the interval of 0 to 3, we'll say time 1, our velocity is positive and our acceleration is negative. So if you plug 1 into this equation, you get a positive answer. And if you plug 1 into this equation, you get a negative answer. And I basically made a sign chart for each interval of time, 0 to 3, 3 to 5, 5 to 7, and then 7 to infinity. And I looked for instances when the sign was the same. So from time 3 to 5, we had matching signs, and from time 7 to infinity, we had matching signs. So that's when we can say that the particle is speeding up, and the particle is slowing down in the other two intervals. All right, moving down, the last question was to sketch a particle path. And this isn't exactly how the particle moves through space. This is just a rough drawing to show what's going on over time. And from time 0 to time 3, we're kind of slowing down and moving to the right. And then from time 3 to time 5, we're moving to the left, but speeding up. And from 5 to 7, we're slowing down, and we're still going to the left, and you can see that because we have negative velocity. And then at time 7, we come to a stop and change directions, and we start moving to the right again. Our velocity is positive, and our acceleration is positive, so we're speeding up. And the word up got cut off right there, but up. Right. Thanks for watching this video. And after this video, you should be able to apply differentiation rules within the context of rate of change. And the most important takeaway is that the derivative of position, so s prime of t, is your velocity function, and the derivative of your velocity function is your acceleration function. And the one thing that students frequently struggle with is the concept of speeding up or slowing down. We are speeding up if acceleration and velocity have the same sign. So if they're both greater than 0 or both less than 0, then we are speeding up. If they're both greater than 0, you could say we're speeding up in the positive direction. And if they're both less than 0, then we're speeding up in the negative direction. The answer to the trivia question is the scroll shown here is found very frequently at the top of some columns, and the most common type of column you'll see this at the top of is the ionic order. I-O-N-I-C, ionic order of Greek architecture.